Good evening, ma'am.
Good evening. So, shall we do some more of areas of parallelograms? 1 minute, I'll share my screen. Can you see? Can you
Yes,
see?
ma'am.
So, areas of parallelograms and triangles.
We are familiar with the concept
Can you hear? Is it audible?
Yes, ma'am.
Okay.
of area related to plane figures. Let's take a closer look at the concept of a planar region and the meaning of the term area of a region. The part of the plane enclosed by a simple closed figure is called planar region. Here, the shaded parts of each plane figure represent a planar region.
So, this is just a plane. It doesn't have thickness.
The measure or magnitude of a planar region is known as the area of the region. Always remember that the magnitude is expressed in a number followed by the unit of area. Consider a rectangle ABCD and a square PQRS. The area of a rectangle is equal to the product of its length and breadth. Therefore, the area of rectangle ABCD is equal to 12 square centimeters, where 12 is the magnitude and square centimeter is the unit of area. The area of a square is equal to the square of one of its sides. Therefore, the area of square PQRS is equal to 9 square centimeters, where 9 is the magnitude and square centimeter is the unit of area. We know that congruent figures have the same shape and size. Now, consider two congruent rectangles. Is there any relationship between the areas of these two rectangles? Both the rectangles cover each other completely. Therefore, they have equal areas. Hence, we conclude that all congruent figures have equal areas. Next, consider the two rectangles ABCD and PQRS having equal areas. Are they congruent?
Are they congruent?
No, ma'am. No, ma'am. No, ma'am.
No.
No, ma'am.
Areas are same. Areas are equal, but they are not congruent because they do not overlap.
Let's look at some of the properties of areas of planar regions. Consider the planar regions formed by the figures P and Q. Observe that the planar regions formed by the figures P and Q overlap each other. Hence, the two figures P and Q are congruent and have equal area. Next, consider the planar regions formed by the figures P and Q. Observe that the planar region T is made up of two non-overlapping planar regions formed by the figures P and Q. Thus, the area of the figure T is equal to the sum of the areas of the figures P and Q. These figures are said to lie on the same base and between the same parallels. Two figures are said to be on the same base and between the same parallels when their bases are common and the vertices opposite to the common base lie on a line parallel to the base. Now, look at some examples. In this figure, the parallelograms ABCD and BECD are on the same base C and between the same parallels AE and DC because their base DC is common and the vertices A and B of parallelogram ABCD and the vertices B and E of parallelogram BECD that are opposite to the common base DC lie on a line AE parallel to the base DC. Similarly, in this figure, parallelogram PQRS and triangle TRS are on the same base SR and between the same parallels PT and SR. Also, in this figure, the triangles DEF and GEF are on the same base EF and between the same parallels EF and DG. Let's identify the figures on the same base and between the same parallels. Here, AF is parallel to DC. Clearly, trapeziums ABCD and EFCD are on the same base DC and between the same parallels AF and DC, as the vertices A, B of ABCD and the vertices E and F of EFCD lie on the line AF, which is parallel to the base DC. In this case, is parallel to SR. The parallelogram PQRS and the trapezium MNRS are on the same base SR and between the same parallels PN and SR, as the vertices P and Q of PQRS and the vertices M and N of MNRS lie on the line PN, which is parallel to the base SR. Here, AD parallel to BC. Triangles ABC and DBC are on the common base BC and between the same parallels AD and DC. In this figure, AP is parallel to, and the parallelogram ABCD and the triangle PCD are on the same base DC and between the same parallels AP and DC. Here, AB is parallel to DC and the quadrilaterals ABCD and EFCD lie on the same base but not between the same parallels, as the vertices E and F of EFCD do not lie on the same line as the vertices A and B of ABCD.
Was that clear?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
When figures are said to be on the
So what is the area? They have asked us to count the squares, but can you see the squares there?
Yes, ma'am.
same base and
Is it
between the same
visible?
parallels. Now, we will establish the relationship between the areas of two parallelograms that lie on the same base and between the same parallels. Find the areas of two parallelograms ABCD and EFCD that lie on the same base DC and between the same parallels EB and DC by the method of counting squares. Use the given formula to find the areas of the parallelograms. In the parallelograms ABCD and EFCD, we find that the number of fully filled squares in both the parallelograms is 20. The number of half-filled squares is 0. The number of more than half-filled squares is 4. Using the formula, we find that the area of each parallelogram ABCD and EFCD is equal to 24 square centimeters.
They have on the parallelograms on a graph sheet and they are counting the number of squares.
Is there any relation between the areas of the parallelograms ABCD and EFCD? Areas of both the parallelograms ABCD and EFCD are equal. Therefore, we conclude that parallelograms on the same base and between the same parallels are equal in area. Let's perform another activity to see how parallelograms on the same base and between the same parallels are equal in area. Consider a parallelogram ABCD. Draw a line segment CE as shown. Take a triangle E1DA congruent to the triangle ECB and place it in such a way that AD coincides with BC. We observe that the parallelograms ABCD and E1ECD are on the same base DC and between the same parallels E1B and DC. Note that the area of the parallelogram ABCD is the sum of the areas of the trapezium AECD and the triangle ECB. And the area of the parallelogram E1ECD is the sum of the areas of the trapezium AECD and the triangle E1DA. But the area of the triangle ECB is equal to the area of the triangle E1DA because they are congruent. Therefore, the area of the parallelogram ABCD is equal to the area of the parallelogram E1ECD.
Did you understand this?
Yes, ma'am.
Yes, ma'am.
Okay.
Let's now prove that parallelograms on the same base and between the same parallels are equal in area. Two parallelograms ABCD and PBCQ are given such that they lie on the same base B and between the same parallels AQ and BC. We need to prove that the area of the parallelogram ABCD is equal to the area of the parallelogram PBCQ.
How can you prove?
By making those triangles congruent.
They are congruent how?
Ma'am, AB is equals to DC.
Ah,
And ED is equal to, ma'am, PB is
Ma'am,
equal to Q, sir.
angle
PB is equal to QC.
PCAB equal to QDC, ma'am.
ah,
Corresponding angles, ma'am.
ah.
Then angle APB equal to DQC, ma'am. They are also
APB equal
corresponding
to-
angles, ma'am. And by
Huh.
AAS, we can prove that, ma'am. AAS, ma'am. Ma'am, angle sum property, we can take angle ABP is equals to angle DCQ.
Angle sum property. How? Angle sum.
Ma'am, angle CAB is equals to QD. Will be equal, no, ma'am, in triangle.
Ah.
Or we can use AAS, ma'am.
Let's begin with the proof. In triangles A and DCQ, AB is equal to DC because the opposite sides of a parallelogram are equal. Angle BAP is equal to angle CDQ as they are corresponding angles. Also, angle BPA is equal to angle CQD as they are corresponding angles. Therefore, by the AAS criterion of triangle ABP is congruent to triangle DCQ. This implies that the area of the triangle DCQ. Now, add the area of the quadrilateral PBCD on both sides of the above equation. We find that the area of the parallelogram ABCD is equal to the area of the parallelogram PBCQ. Therefore, the theorem is proved. Now, prove that the area of a parallelogram is the product of its base and the corresponding altitude. A parallelogram ABCD is given in which AL is perpendicular to CD. We prove that the area of the parallelogram ABCD is equal to the product of its base DC and altitude AL.
How can you prove? Area of ABCD. DC into AL.
Complete the rectangle EFCD by drawing CF perpendicular to AB and DE perpendicular to AB.
Now, see the construction. What is the area of the rectangle DCFE?
Ma'am, DF into DC, ma'am.
DC into DF.
Into DF.
DC into
DE, ma'am.
DE, ma'am. DE, ma'am.
huh. So DC we have got. So DE must become equal to AL, right?
Yes, ma'am.
Are they equal? AL and DE.
Yes, ma'am.
Yes, ma'am.
Why? How?
Let's begin with the proof. Here, the parallelogram ABCD and the rectangle EFCD are on the same base DC and between the same parallels EB and DC. Since a rectangle is also a parallelogram, the area of the parallelogram ABCD is equal to the area of the rectangle EFCD, which is the product of its length DC and breadth FC. Denote this as equation 1. Also, AFCL is a rectangle because AL is perpendicular to DC. So we get AL is equal to FC. Denote this as equation 2. Therefore, from equations 1 and 2, we get that the area of the parallelogram ABCD is equal to the product of its base DC and the corresponding altitude AL.
Got it?
Yes, ma'am.
Yes?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, prove the converse of theorem 1, that is, parallelograms on the same base or equal bases and with equal areas lie between the same parallels. It is given that the area of the parallelogram ABCD is equal to the area of the parallelogram EBCF. We need to prove that ED is parallel to BC. Draw AL and EM perpendicular to BC.
So how can you prove ED is parallel to BC? Areas of ABCD equal to area of EBCF. What is the area of ABCD? Area of
Ma'am, AL
ABCD?
into BC, ma'am.
BC into AL, ma'am.
EBCF?
BC into AL, ma'am.
BC
No,
into
ma'am.
AL.
Or BC into EM, ma'am.
BC into
Yeah.
EM, ma'am.
Whichever. EM equal to AL, no?
Yes,
We have
ma'am.
to prove that it is parallel. When can you call the lines parallel?
Let's begin with the proof. The area of the parallelogram ABCD is equal.
When can you say the lines are parallel?
When they do not intersect.
But
When
we
they
are
extend it further.
proving logically, no?
The corresponding angles are equal.
And ma'am,
Yes,
the
corresponding.
distance between the two.
Alternate.
Huh.
To the product of its base BC and altitude AL. Denote this as equation 1. Similarly, the area of the parallelogram EBCF is equal to BC into EM. Denote this as equation 2. But it is given that the areas of the parallelograms ABCD and EBCF are equal.
So what can you say from this?
AL is equal to EM, ma'am.
Huh.
Therefore, from equations 1 and 2, we get AL is equal to EM. Therefore, ED is parallel to BC because AL and EM are equal altitudes.
They are the perpendiculars. Perpendicular distance between the two lines are equal. So the lines are parallel.
Let's begin with the proof. The area of the Let's perform an activity to find the relation between the areas of a parallelogram and a triangle with the same base and between the same parallels. Consider a parallelogram ABCD and a triangle PAB. We see that PAB and the parallelogram ABCD are on the same base AB. and between the same parallels PC and AB. Triangle PAB overlaps triangle ABC completely. Therefore, triangles PAB, ABC are congruent. The area of the triangle PAB is equal to ABC. Also, observe that triangle ABC overlaps triangle ADC completely. Therefore, the area of the triangle ABC is equal to the area of the triangle ADC. Therefore, the area of the parallelogram AB is twice the area of the triangle ABC. But the area of the triangle ABC is equal to the area of the triangle PAB. Therefore, the area of the parallelogram ABCD is twice the area of the triangle PAB.
You understand?
Yes, ma'am.
Yes, ma'am.
Consider an example to prove that the area of a triangle is equal to half the area of a parallelogram if the triangle and the parallelogram are on the same base and between the same parallels, and parallelogram ABCD are given such that they lie on the same base AB and E and PC. Area of the parallelogram ABCDB half the.
So how can you prove? Construction is draw BQ parallel to AP and get one parallelogram ABQP. What is the area of ABQP equal to?
ABCD, ma'am.
ABCD.
Correct. Now, ABQ is 2 times APB, right?
Yes, ma'am.
Ma'am.
Yes, ma'am.
So APB is half of ABC. Correct?
Yes, ma'am.
Now, the parallelograms ABCD and QP are on the same base AB and between the same parallels AB and PC. Therefore, the area of the parallelogram BCD is equal to the area of the parallelogram ABQP. Note this as equation 1. But triangle PAB is congruent to triangle BQP, and the diagonal of a parallelogram divides it into two congruent triangles. Therefore, the area of the triangle PAB is equal to the area of the triangle BQP. This implies that the area of the triangle PAB is half the area of the parallelogram ABQP. Therefore, the area of the triangle PAB is half the area of the parallelogram ABCD.
Is it clear?
Yes,
Yes,
ma'am.
ma'am.
Example 2. If in a
Excuse me, ma'am.
parallelogram, example 2.
Yes?
Ma'am, I
Yes.
solved it in some other way. I wanted to know whether it is correct.
Tell me. Tell.
Ma'am, first I wrote the area of ABP is equals to area of ABCD to
Now,
prove.
the parallelograms.
Huh. 1
Then,
minute.
ma'am,
1
we
minute.
know that.
Now,
Huh.
consider an example to prove that the area of a triangle is equal to half the area of a parallelogram if the triangle and the parallelogram are on the same base and between the same parallels. Triangle ABP.
Huh. Tell me now.
Ma'am, we know that they lie on the same base and on the same parallels. So their height will be same, ma'am. That base is same, ma'am. This is given. So the area of triangle APB is equals to half base into height is equals to the area of parallelogram ABCD base into height. Here we know that, ma'am, in both the triangles height and base are equal. Therefore the and half will remain in triangle, ma'am. So half area of the parallelogram is equal to the area of parallelogram is equal to half area of triangle, ma'am.
Area of parallelogram equal to half area or area of triangle?
The total area of parallelogram is equal to the triangle or the area of triangle, ma'am. That means two area of the same triangle is equal to the total area of the parallelogram, ma'am.
Yes, correct, correct. You can prove like that.
Now, the
Okay, thank you, ma'am.
example 2.
Now solve this question. You have to find AD. Base is 10, height is 5. What is the area of ABCD?
Ma'am, I got it.
Huh,
50, ma'am. 50, ma'am.
50. Huh. What is AD?
50, ma'am.
AD?
Ma'am, 612.
Ma'am, we have to find AD.
Yes. We have to,
DC is
the
equal
area
to 10
of
centimeter, ma'am.
ABCD with AD at the base will be AD into 8. AD into 8 equal to 50. Correct?
Yes, ma'am.
Yes,
So
ma'am.
how much is AD?
6.25, ma'am.
6.25.
6.25, ma'am.
Okay.
If in a parallelogram ABCD, AB is equal to 10 cm. Also, the parallelogram ABCD is equal to AD to BF. Example 3. If P, Q, R and S are respectively the midpoints of the sides AB, BC, CD and DA of a parallelogram ABCD, show that the quadrilateral PQRS is a parallelogram and its area is half the area of the parallelogram ABCD. It is given that P, Q, R and S are respectively the midpoints of AB, BC, CD and DA of a parallelogram ABCD. We have to show RS is a parallelogram and also that the area of the parallelogram PQRS is equal to half the area of the parallelogram ABC. Join BD and SQ.
How will you prove? To prove that PQRS is a parallelogram.
SP is equal to half of DB, ma'am. And RQ is equal to half of DB, ma'am. SP equal to
Correct.
RQ, ma'am. And again, SP is parallel to DB and RQ is parallel to DB. So PS is equal
Correct.
to PS is parallel to QR. So it is a parallelogram.
Correct. Now your next part is area of PQRS is half area ABCD. Why? Yes, they have joined SQ.
Ma'am, in parallelogram ABQS, ma'am, the area of the
Hmm.
triangle SP is equal to half of the area of ABQS, ma'am.
Correct.
Similarly, we can prove, ma'am, area of triangle SRQ is equals to half of the area of parallelogram SDCQ, ma'am.
Huh.
Then
By taking half
from
common.
equation number 1, this we can take equation number 2, ma'am. And the area of triangle PSQ is half of area of parallelogram ASQB, ma'am. That is equation
Huh.
number 1. By adding equation number 1 and 2, we get area of parallelogram, area of a quadrilateral PQRS is half of area of parallelogram ABCD, ma'am.
Consider a triangle ABD in which P and S are the mid. Now, ABCD is a parallelogram. This implies that AD is equal and parallel to BC. Adding equations 3 and 4, we get the sum of the areas of triangles PSQ and RSQ. Example 4. In the given figure, XY is a line parallel to side BC of triangle ABC. BE parallel to AC and CF is parallel to AB. Prove that the area of the triangle ABE is equal to the area of the triangle ACF. It is given that XY is a line parallel to side BC of the triangle ABC. BE is parallel to AC and CF is parallel to AB. We have to prove that the area of the triangle ABE is equal to the area of the triangle ACF.
So how do you prove?
Now, join AE.
How do you prove ABE equal to ACF? Now take the lines which are parallel. XY is parallel to BC and BE is parallel to CF. AC. BE is parallel to AC. Sorry.
Ma'am, in
Huh.
parallelogram EYCB, ma'am.
EY.
Ma'am, area of
EYCB.
parallelogram EYCB, ma'am. Area of EXB plus area of XYCB, ma'am.
Huh.
And area of parallelogram XFCB, ma'am. Area
Huh.
of XYCB plus area of YFC, ma'am.
Huh.
We take this as equation number 2, ma'am.
Huh.
In
area
both
of
the equation,
EXB. Huh.
in
Huh.
both the equation, XYCB is the common, ma'am.
Correct.
So we get area of EXB is equal to area of FYC, ma'am.
Okay. Now we have to get ABE. What about AXE? AXE, AYF.
E and AF. Proof. It is given.
See, you have to get ABE, right? You have got BXE. What about AXE? Which line is parallel there? Which line is parallel? AXE and AYE. F. Only one triangle you will get, right? Hello?
Yes, ma'am.
EB is parallel to AC. Now on EB, same base, you have EAB and any other triangle? Triangles on the same base and between the same parallels. Now see, you have used XY parallel to BC, EF parallel to BC. Now you have to use AC parallel to EB and EFC parallel to AB. You have to prove that area of AXE equal to AYF.
Repeat, ma'am.
You have to prove, see now already you have proved area of EXB equal to YC. You have proved. Now
Yes, ma'am.
you have to AXE and AYF. You have to prove they are equal. Then if you add 1 and 2, you will get AEB, AFC.
Ma'am, area of triangle AYE is equal to area of triangle AXF, ma'am.
How? What is the reason? How they are equal? See, their base here is XE or AE or AX. How they are equal? BE is parallel to AC. And AB parallel to FC.
That XY is parallel to BC and BE is parallel to AC. This implies that EY is parallel to BC and BE is parallel to CY. Therefore, quadrilateral BCYE is a parallelogram.
This is what you told.
But parallelograms BCFX and BCYE are on the same base BC and between the same parallels BC and EF. Therefore, the area of the parallelogram BCFX is equal to the area of the parallelogram BCYE. Denote this as equation 3. From equations 1, 2 and 3, we get that the area of the triangle ABE is equal to the area of the triangle ACF.
What was the second equation?
Triangle ABE and parallelogram BCYE are on the same base, BE, and between the same parallels, BE and AC. Therefore, the area of the triangle ABE is half the area of the parallelogram BCYE. Denote this as equation 1. Now, CF is parallel to AB and
You agree?
Yes, ma'am.
You agree?
Yes, ma'am.
Here, BCYE is a parallelogram. ABE is a triangle on the same base BE. So area of ABE is half of area of BCYE. And this side area of AFC,
C.
half area.
BCFX, ma'am.
BCFX. So from that we will get.
but parallelograms BCFX and BCYE are on the same base BC and between the same parallels BC and EF. Therefore, the area of the parallelogram BCFX is equal to the area of the parallelogram BCYE. Denote this as equal. From equations 1, 2 and 3, we get that the area of the triangle AB is equal to the area of the triangle ACF.
Here they have not taken the triangle BXE, correct?
Yes, ma'am.
And CYF they have not taken. They have taken area of triangle is half the area of the parallelogram.
Parallels of a parallelogram D intersect at a point O. Through O is drawn to intersect AB at P and BC at Q. Show that PQ divides the parallelogram ABCD two parts of equal area. It is given that the diagonals AC and BD of the parallelogram ABCD intersect at a point O. Through O, a line is drawn to intersect AD at P and BC at Q. We have to prove that the area of the quadrilateral APQB is equal to the area of the quadrilateral QCD.
How will you prove? APQB equal to PQCD. Angle 3 equal to
Angle 2.
Angle 4, ma'am.
Angle 4, ma'am.
1 equal
1 equal to
ma'am.
2, ma'am.
AO equal to
OC, ma'am.
OC,
so triangles are
congruent
Congruent.
and equal in area.
typicity. We have to prove
Ma'am,
that
area
triangle.
Uh,
Area of APO equal to QOC.
PO equal
Yes,
to
ma'am.
OQ.
We have to prove that area of APQB equal to PQCD. AO be congruent to DOC.
Yes, ma'am.
Yes, ma'am.
And remaining part is BOQ and POD.
Yes, ma'am.
How? DO equal to BO.
And PO is equal to OQ, ma'am, by CPCT.
And PDO equal to
POQ, ma'am. OQC, ma'am. OQB, ma'am.
PDO.
And we can take the vertically opposite angles.
We can take POD equal to BOQ. Correct. We can also take PDO equal to
OBQ, ma'am.
OBQ. So from all this, we get the area APQB equal to PQCD.
In a parallelogram ABCD, the area of the triangle ABC is equal to the area of the triangle ADC, as the diagonal of a parallelogram divides it into two triangles of equal area. This implies that the area of the triangle COQ plus the area of the quadrilateral ABQO is equal to the area of the triangle AOP plus the area of the quadrilateral CDPO. Now, in triangles COQ and AOP, AO is equal to OC, as the diagonals of a parallelogram bisect each other. Angle 1 is equal to angle 2 because they are vertically opposite angles. Angle 3 is equal to angle 4 as they are alternate angles. Therefore, by the ASA criterion of congruency, the triangle COQ is congruent to the triangle AOP. Since triangle COQ is congruent to triangle AOP and congruent triangles are equal in area, the area of the triangle COQ is equal to the area of the triangle AOP. Now, the area of the triangle COQ plus the area of the quadrilateral ABQO is equal to the area of the triangle AOP plus the area of the quadrilateral CDPO. From equation 1, we get that the area of the triangle AOP plus the area of the quadrilateral ABQO is equal to the area of the triangle COQ plus the area of the quadrilateral CDPO. Therefore, the area of the quadrilateral APQB is equal to the area of the quadrilateral PQCD.
Is it clear?
Yes, ma'am.
Try these questions. Their answers on the next page.
You want to do this?
Yes, ma'am.
Take a shot. I will also send this in WhatsApp. Okay? 3
Yes,
questions.
ma'am.
Okay?
Okay, ma'am.
Here are the answers, and
Recall that two figures are said to be on the same base and between the same parallels if they have the common base and the vertices opposite to the common base of each figure lie on a line parallel to the base. Here we have two triangles, ABC and DBC. These lie on the same base, BC, and between the same parallels, AD and BC.
So, what do you know about that?
Area of triangle ABC equal to area of triangle ADBC, ma'am.
Correct. Because they have the same base and they are between the same parallels, height will be the same, base is the same.
Well,
You will get their area.
Let's find the relationship between two triangles that lie on the same base and between the same parallels. Here, AB is parallel to DC. Now consider two triangles, C and BC, that lie on the same base DC and between the same parallels AB and DC. Observe that the triangle ADC overlaps the triangle BDC completely. Hence, ADC and BDC are congruent. Therefore, the area of the triangle ADC is equal to the area of the triangle BDC. Now, let's prove that triangles on the same base and between the same parallels are equal in area. It is given that two triangles, ABC and DBC, are on the same base BC and F and BC. We need to prove that the area of the triangle C is equal to the area of the triangle. Draw BF parallel to CA through B, intersecting DA produced in F. Also, draw CE parallel to BD through C, intersecting AD produced in E.
So what figures are BCAF and BCEA? ED.
Parallelogram.
BCAD, BCAF. Parallelogram. So their areas
They
will
have
be
equal area.
equal. And AB is the diagonal for BCAF and DC is the diagonal for BCED. So half of that will be half the area of BC equal to BCA. Correct?
Yes,
Yes.
ma'am.
So their areas will be area of BD ABC equal to area of BC. Not the only way of proving. You can prove in different
Let's
ways.
start with the proof. By construction, is parallel to CA, and it is given that BC is parallel to FA. Since both pairs of the opposite sides of the quadrilateral BCAF are parallel, it is a parallelogram. Similarly, the quadrilateral BCED parallelogram. Now, both parallelograms have the same base BC and between the same parallels FE and BC. Therefore, the area of the parallelogram CED equal to the area of the parallelogram BCAF. Denote this as equation 1. We know that a diagonal of a parallelogram divides it into two triangles of equal area. Therefore, the area of the triangle ABC is equal to half the area of the parallelogram BCAF. Denote this as equation 2. Similarly, the area of the triangle DBC is equal to half the area of the parallelogram BCED. Denote this as equation 3. Hence, from equations 1, 2, and 3, we get that the area of the triangle ABC is equal to the area of the triangle DBC.
Got it?
Yes, ma'am.
Yes.
Yes, ma'am.
Now
Yes,
time is up. Shall we close today's lesson?
Okay, ma'am. Yes, ma'am. Yes, ma'am.
Good night.
Bye, ma'am. Thank you,
Bye.
ma'am. Good night, ma'am. Bye, ma'am.
Bye.
Thank you, ma'am. Bye, ma'am.
Bye.